compositions of linear operators as functions, so consecutive computations, consecutive applications of functions. Okay, so every two functions, if the input-output spaces match, can be composed. Okay, so this is what I'm talking about. These two match. Okay, so I go from F, from R to R2, then the output of F is plugged into G. Remember how compositions are formed. Only in pre-calculus you talked about numerical functions for the most part. In this is more complicated. But even though the problem number one didn't work out, but you spend a little bit of time thinking about it, you know what I'm talking about. It is about consecutive applications of those transformations. Okay, so you know what it is. It is the output of the first becomes the input of the second, and the output of the second becomes the input of the third, and as many times as necessary. Okay? Okay, let's turn away from the homework and towards the new topic. So, like I said, it is just as challenging. So understanding compositions is crucial, but I think it is if you just give it some thought or just face a lot of those problems, you will see it's no big deal. Consecutive applications of functions, well, especially if you are into programming. You know, apply one function, then the next one, it's like a black box, and then the output in the second consecutive programs are applied. Okay. Algebraically, it means substitution. Looks a little bit awkward, more awkward than the diagram, but that's what it is. So in particular, if the notation that we use is G circle F for compositions, but in reality, what is it? It is substitution. So like this. So look at it. I start with X. Okay, then I apply F. This is my out. The first output is here, and then I apply G. Okay. So this is pretty much the definition of a composition as of any function of a function of any nature. So it could apply if X is a number. Well, then you go through numbers. If these could be vectors, could be multidimensional vectors, or anything imaginable works out here. Okay, data, whatever. Okay, so you do something to the object, then it becomes the output. The output becomes the input of the next function. Okay, so the only thing is that now we know what XR is or are these vectors, and in the meantime, F and G are linear operators, which works out nicely because the output of a linear operator is another vector. Okay, so vector, 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 these are the outputs. So to begin with, so that up to this point, the treatment is entirely theoretical and not necessarily has anything to do with linear algebra. But then what is there now? We cannot really leave it as this because it's so general that it's virtually useless. But because we narrow down the scope of both the input-output and the nature of the function, we can say a lot about the compositions. And the key to it is here that both F and G are, in fact, can be represented by matrices. Okay, so in algebra, they might have some complicated formulas. Or in programming, it could some complicated multi-step procedures, but we are in a better place. We're just talking about linear operators, and if a dimension is just 2, you're going to have just two by 2 matrices. That's all for the time being. Okay, and then it is nice to discover that not hard to demonstrate that in fact the composition of two linear operators is a linear operator. Okay. Rotation followed by a flip. Okay, it is a linear operator. Just once again what you saw in that homework problem number 1, or you have stretch, and then followed by another stretch in a different direction. Okay, what is it? It's still a linear operator. Okay, and then we use this. That's the same idea from not a long time ago, that every linear operator is also represented by a matrix. So we have 3 2x2 matrices. We have 3 2x2 matrices, and the relation between those 3 matrices turns out to be very familiar. It is multiplication. So that is the meaning of multiplication of matrices. It's really not about, it's not like multiplication of numbers, hardly. It is more like compositions. Okay, it's just a coincidence of history that we decided to call matrix multiplication. We could have just as well called it matrix composition. Okay, it is better because then you always remember that after all, matrix represents a linear operator, and as such it is a function, and as such it follows, it can be subject to a lot of things that functions are subject to. So things such as compositions, things such as inversion, identity, the image, pre-image, whatever, one-to-one, onto, bijection, all of these things that you might remember from pre-calculus as they were applied to numerical functions. Now they are equally applied to linear operators. So the example, as you can see here, the composition, I carried out one computation here of well, just in case one more multiplication of matrices, just to remind you that it is computed one at a time. So one row, one column produces one entry. Okay, and that's how we got 4 entries. In this particular case, 2x2 by 2x2, so you have to carry out 4 computations. So 4 computations, each of which contains 2 multiplication and 1 addition, right? So because after all, what we're doing here, if not the dot product, right? So that product ends up here. Okay, just to remind you what this is about. Okay, so we are in a very good place. We can compose linear operators in a very easy way. Okay, so we don't have to do substitution. All we have to do, substitution, which is over there at the top on the right, we just multiply matrices. It is cumbersome if you do it by hand, but really it is very straightforward. Okay. Okay, so we'll get back to that, but with the okay, no, we'll continue with this. So okay, so we need to discuss this the issue of hold on, where is the I lost why we do it, why we care about, I think I had it here. Well, okay, let me say that again. Is what we care about is the equation. Why we care about compositions? Because it allows us to understand the meaning of the inverse. So what is the inverse of a function? Okay, but really that is a wrong question. The right question is what kind of function, even if before we understand what it is, what kind of function has the inverse? Remember that? From pre-calculus. So this always helps.
Is it
onto? So why onto? Because if I missed one entry over here, and there is no arrow arriving to this point over here, when I try to reverse the arrows, that's what inverse is, reversing the arrows like this. Okay? If one is missing, no arrow arriving to this point, then there will be no arrow starting from this point. So there is no inverse. So it has to be onto, but what else can happen? 1-to-1. So this is what can happen. There might be 2 points, 2 arrows arriving to the same spot over here, particular y. 2 arrows arriving. So once again, no inverse, because once we reverse it, what happens? Right. Well, which one? We don't really have a choice, right? So we will have to pick both because that's the way it has to work. We cannot just throw it out. It will become a different function altogether. So 1-to-1 and onto, which together is called, if you like that word, I remember especially like, it's called either a bijection. Another word for it is 1-to-1 correspondence, which is long but descriptive. Bijection is fine. I think it is short to the point. Okay, so however, we have to understand this more carefully because so we can translate it into the language of matrices. So the function is 1-to-1 onto. It is bijection, which means that for every input there is for every output there is only one input, and there's exactly one input. Okay, so for every y there is exactly one x. So y is equal to f of x. Okay. So if this is satisfied, then we know whether the inverse exists even though we haven't said what that is. So remember the definition of the inverse. The definition of the inverse.
F of -1, f of x equals x.
Yeah. So say it again. F of
f -1
yeah.
of f of x equals x.
Okay, in other words, we can have that illustration if like this once again. So if I have my f's going like this, and once again 1-to-1 onto, there is nothing missing, no arrows arriving to the same spot. I am reversing them to acquire the inverse. So this is f inverse. And then what this equation says is that if we start with x, here we will make a full trip like this. Full trip right back like this. So this is my x over here. This is my full trip. Okay, for each x. For each x in x. Well, there's a second half of this.
The second, the y one.
Yeah. So what is it?
F of -1, f of y equals y.
Yes, say it again.
Like the f.
F?
Of -1.
No, f.
Oh yeah, f of -1
right.
of y equals x.
For each y.
Yeah, I forgot.
Okay, so this is the definition of the inverse, f inverse. Inverse of f is defined as a function that satisfies these two inequalities when the function is two equations, not really equations but identities, and then when this is the case we call this the inverse. There's only one inverse, and well, everything is fine, but it is explained through composition. So now we can translate this into the language of matrices and linear operators. So suppose these are linear operators, then everything, all the definitions and all the analysis applies. But it is more specific. So because we can now express everything in terms of matrices. So f is a linear operator, and we want it to be a bijection. Suppose so that then as you can see, bijections will become a big issue because then everything is invertible. Then The meaning F inverse is also a linear operator that satisfies those equations. Okay, what does the first equation become? Remember, we are now talking about linear operator slash a matrix. So in other words, we're talking about two matrices. Linear operator matrix is the same thing as long as the basis is fixed. Okay, so how do we write out the these equations? Well, actually, it doesn't have to be necessarily. We don't have to jump to matrices. We could express these equations, identities at the top with the circle notation. So F inverse circle F is equal to what? No, I don't want to use the variable anymore. What kind of function is it? It's not 1, but there's a word for it. What? Well, you see, we look at the top. Okay, so it is a composition of F and F inverse. It is a function, and that function is described in the right-hand side of that equation. What kind of function is that? Look at the function on the right.
Onto.
No, not just onto. The function on the right is it takes x to x. What do we call that function? The identity, that's right. So this is the identity function on x. Okay? Or if you prefer matrices, then for matrices it will be exactly the same thing. Notation is exactly the same. FF, and there is the identity matrix, only we denote it by simply I. So ID stands for identity function or linear operator, but for matrices it corresponds to a matrix. Remember what it is. It is a matrix with all zeros except one on the diagonal. Okay, and so like this. And this is a matrix multiplication. So then the inverse matrix satisfies this equation on the right. The matrix multiplication with the F will produce the identity matrix, and then we have the same story for the second equation. So F composition F inverse is equal to the identity. Okay, even though, well, once again, keep in mind these are two different spaces, so I could code X and Y probably, yeah. Okay, so they possibly different spaces in some sense, but that's okay. The dimensions will be the same. These are in fact square matrices, and I have multiplying them. Come on. Is equal to I, and it is the exact same matrix. So all of these are n by n, where what is n? N is the dimension of the space x, which is the same as the dimension of the space y. Otherwise, we would not be able to have a bijection. That is also to be demonstrated, but we will just accept this. So once again, you can only have a bijection between two Euclidean spaces of the same dimension. And in which case the matrices are square matrices, n by n, and they satisfy these identities on the right. Okay, so then first of all, let me quickly mention why we care. And the answer is, I mentioned that before, but let's do it again anyway. If we need to solve a system of linear equations, fx is equal to b, right? It is where everything starts in linear algebra anyway. We need to find x for a given b. F is our matrix of coefficients, b is the right-hand side. How do we solve it? Well, like this. X is equal to f inverse of b. Done. So if you have the inverse, then you can always just whatever b is, you just substitute it with the inverse, and you have the answer. Right? Okay, so if it is convenient to find the inverse rather than solve one particular system of equations as you would normally have done, right? You have your matrix naturally, but you also have B provided in a specific way. Say I have 1, 2, 3, 4, and then you have 1, 2 here. That's my augmented matrix, and then I have another one with the same matrix, but the right-hand side is different, like this. So normally, how would you do it? You would solve them separately. This time, if you have the inverse, you don't have to. You find and then you apply that inverse twice. So you have, if this matrix is F, and okay, then the answer would be X is equal to F inverse of 1, 2. Or for the second problem, X is equal to F inverse of 2, 5. Okay, so that's an advantage. So for the same matrix of coefficients, if you can solve at this point any equation that is given to you, no matter what the right hand side is. Okay, so that is a convenience. So it's like finding the inverse for an exponential function and keep using it. That's the logarithm for you. Okay, so what remains is so the problem certainly will be addressed if we have time to actually how to find the inverse, but it's not really that complicated if the dimension is small. Then there is a solution, A, B, C, D, inverse. There is a solution, and it is, let's see if we can guess what it is. So what is it? Okay, let's try to guess from examples that we have. Okay, for example, as to begin with, F is equal to, say, KID. So it is a stretch, uniform stretch in all directions. Okay, so what's the F inverse? So what's the inverse? What transformation of the plane undoes the effect of stretching? What?
Like division by.
No, stretching. What's the opposite? What?
Condensing.
Condensing, yeah, shrinking. So what's the formula of shrinking? So we stretch by a factor of 2.
Or divided by half.
Yeah, 1 over k, right. 1 over KID. 1 over KID, which means that it will have a k on the diagonal or 1 over k on the diagonal. Okay, so as you can see, it is not entirely predictable what the inverse is. So then say KK 0, 0, K inverse is equal to, in fact, I swear I'm not doing this. The pen doing this. Inverse is equal to 1 over K 0, 0, 1 over k. Okay, so that is one example. Another example, how about the flip? So this is a stretch. Now another example of flip. How about, well, it doesn't matter which flip. Let's pick the easiest flip around the x-axis, around the y-axis. It will be what? The matrix will be negative 1, 0, 0, 1, right? What's its inverse? The same, that's right. It is the same. Another flip does the So the other effect, the other flips, all flips are like this. So it doesn't matter around which axis you flip, you repeat it yourself. So two more I could think about the other flip, about the y-axis, about the x-axis it will be 1, 0, 0, -1. Its inverse is itself, again, 1, 0, 0, -1. And finally the flip about the origin, it will be -1, 0, 0, -1. And its inverse is once again -1, 0, 0, -1. Okay, as you can see, not a lot is happening with the